上课啊。The last time we discussed the length of finger. We also discussed spin, chirality, and adhesion. So we talked about first of the vector axis. And we mentioned there is a anomaly. Yeah, someone asked after the lecture about more details about the anomaly. Yeah, we didn't discuss too much about anomaly. So later, maybe if we have time, we'll come back to discussion. And in the end of the last lecture, we discussed the Majorana fermion. In particular, we figure out how to establish the theory, how to define the theory of Majorana fermions. And for this part, we particularly discussed in detail the charge conjugation, or the charge conjugation for spinors. As we can see, for different spinors, this conjugation may be different. Okay? Act on different fermions, this charge conjugation may be different. And let's continue to discuss the spinors. So today, we're going to try to quantize the spinors. So before that, we have to find the solution that we did for scalars and also maxwell fields. So before we quantize these fields, we have to find first solve this classical equation of motion. So today, yeah, I want to quantize this. You're welcome. So for this purpose, first solve the equation of motion. Okay. And let's first write down the equation of motion. The first question is try to find solutions. Okay. As you can see, this is the first order equation. This is the first order differential equation. Find the solutions. What can we do? First observation is we mentioned some time ago. If you act the a gamma partial plus m from the left, then you get the Klein-Gordon equation, right? You get Klein-Gordon equation. So because of that, so similar to the Klein-Gordon equation, one can try to find the so-called plane wave equation, which means that because from this equation we can get the Klein-Gordon equation, which means that there should be such a solution that looks like plane wave, okay? Right? Because this part is what we already saw from Klein-Gordon in solving the Klein-Gordon equation, okay? This can be plus or minus, right? Is the positive frequency or negative frequency, okay? But this is a spinner, okay? This is certainly a number, right? Or a scalar if you want, because it's p dot x. So the coefficient must respond to the spinner structure, right? Right? If you want to claim there is such kind of solution, to determine the unfixed coefficient, you have to put some coefficient, which is a spinner, okay? So let's do this. So let's plug in this ansatz into the equation motion, okay? Plug in. We also mentioned there are different bases, okay, to represent this gamma matrix. So here, let's choose the wire base, for example. In wire bases, the gamma matrix is written as 0, 0, sigma mu, sigma bar mu, okay? And sigma mu defined as 1 sigma I sigma vector, sigma mu bar defined as 1 minus sigma vector. Okay. So the simplest way is just you plug in and try to solve the equation. So you plug in this ansatz together with this gamma matrix. So what do? You get gamma. You get make this more clear. So you get gamma mu minus m act on u p equals to minus m e mu sigma mu p mu sigma mu for act on u. Okay. And this equals to 0. Okay, this equals to 0. Right? Plug in into equation of motion. So you get an equation for this UP. U is a p-dependent linear coefficient. So as you can see, this is a matrix equation. Okay, this is a matrix equation. This is a matrix, and this box is a 4x4 matrix. Okay, and this U is a spinner. There is a 4-component object. Okay? We have to find the solution for this U. So how to find the solution? Right? That's the question. How to find the solution for U? So let me first present the compact solution. I'm trying to explain how we get it. Okay. So the solution for UP is UP equals group square root E dot sigma square root E dot sigma bar this is two components. Constant in okay, so this is the compact solution, but of course it's not a one step. It's not easy. You can directly see this is the final solution. But in order to solve it, in order to find this solution, we can split the problem for a few steps. For example, we want to find a p-dependent complete solution for UP for this equation. Okay. The first thing we can do is we consider the first step we can do is step 1. We can do is we consider the rest free. Right? Because the problem is to find a p-dependent U. Now we can first find the solution p, because p in different frame, p taking different values. Okay, we can first find the solution in the rest frame. Why? Because it's simple, right? In the rest frame, there's no momentum. Okay, there's no momentum. It's static. Okay, rest frame is static. There's no momentum. So in that case, what is p? In that case, what is p? So pu will be, for massive particle, it will be the m0, 0, 0. All right? This is our full momentum. Is it clear? So in this case, this equation simplifies. This case, this equation simplifies. See? Because only p naught has the non-trivial value, or other is 0. Okay? So these two terms become p naught times sigma 0, right? So what is sigma 0? Yeah, sigma 0 is 1. Sigma 0 is 1. So you get what do you get? So you get a minus m, and minus m, right? You see? That's what you get. Therefore, the equation becomes minus 1 plus 1 plus 1 minus 1 x on u equals to 0. You see? Okay. So what is the solution for this equation? Because right hand side is 0, the all constant they can be thrown away. Okay. So what is the solution for this equation? This is the 2x2 matrix together. This is also 2x2 matrix. This is 2x2 matrix. 2x2 matrix. So this is a 4x4, and this is a 4 component. object U. What's the solution for this U?
Plus minus 9.
Right. So the solution for this equation is simply sounds like looks like this. Okay. See, we want this C to denote this two-component part. Okay. So if this two-component object equals to the lower half, okay, then you can check this is always the solution, right? It doesn't matter which two-component object exists here, stay here, okay? Can be arbitrary, okay? Can be arbitrary. For any good spinner. Any good. Okay. Now, then we can do the boost, right? Then we can boost to the finite P, all right? Because you get the one frame solution. If you know how to boost your solution, okay, then you know the general result. Okay, and in the last lecture we do learn, indeed, we learned how to boost the solution because we know how to do the Lorentz transformation of spinner. Okay. Then you boost to a general frame, you get the solution for finite P. Right? That's one way. Of course, there are alternative ways. For example, using some trick to find the solutions. But in the end, you come to the same answer, which solution looks like this. Now, in this solution, there is a structure looks like a square root. It looks like a square root. This P dot sigma is still a matrix, okay? It's still a matrix, right? Because P dot sigma is contract of the mu indices, okay? And P is a number. Sigma is a matrix. So P dot sigma is still a matrix. So do you know how to take a square root of a matrix?
You have eigenvalue. Yeah, diagonalize it and take the square root of the diagonalized matrix.
That's right. So in order to take a square root of a matrix, you first diagonalize it. Okay, you can just take the square root of the eigenvalues. Okay, then you go back and choose. That's what you define mathematically. The square root of matrix. Okay. So here the square root is essentially the square root of the matrix. Okay. Okay, so for example, you can also try to see if you choose to work in a slightly general frame. Let's say you have only a momentum on x, y, z in the z direction. Okay, in the z direction. So in this frame, let's try to switch to another slightly general frame to see the solution. Okay, in order to justify the final answer. So in this case, P dot sigma, as said, P dot sigma is P mu sigma mu. Okay. So in this case, P mu is two components. It's not trivial. The first component and the last component. Okay. Okay. So we have to take into account the sigma 0 and the sigma 3, right? Sigma 0 and sigma 3. So if we do that, we'll get E minus P V, E plus E 0. Okay? And you got P dot sigma bar with E plus P V, E minus P. Okay? So now you solve this equation. Solve this equation. For that, for this structure, we plug into here. Plug into here. What we find is UP is UP is something like E minus E square root E plus E times D, and the lower half is E plus E square root E minus PV and D, and then put it together. Okay, and okay. Yeah, you can check. This is this UP is the solution for that choosing of P mu, and you almost get you can. So you can justify indeed there's a square root in this case, right? There's a square root because in this case P dot sigma is because this part is you just take a square root of this. This part is just take a square root of this part, right? So in this case it's just a diagonal, so you can easily take a square root because the matrix is diagonal matrix. In general, you first diagonalize it, okay, and then take a square root and then go back. That's mathematical definition of the square root for a given general matrix. Okay. So combine into these two particular choice of the frame, eventually, and also combine with the boost to find the P. Eventually, you can get this compact solution, final solution for this UP. This UP. But what we did for scalar case, there's another piece, right? So we call this part with the convention minus in front. We call this is part of the positive frequency. So there is also a negative frequency part, okay, with a plus in front here. So there's another piece. There's another piece. So for the negative frequency part, let's use a different Vp times the plus I P dot I, and plug into the equation of motion, try to solve it, and you find that there is a Vp equals to the reference of P or sigma eta and sigma bar eta. Okay, now eta is again an arbitrary two spin. Okay, it's an arbitrary constant two spin. And then you can straightforwardly to check, like what we did for this U. Okay, for example, you can check in this raster frame. This is raster frame. You can check. You can check. In this case, this raster frame, you can plug in the equation of motion and find the V equal to eta minus eta will be the solution, right? Will be the solution. Now here it becomes minus 1, minus 1, minus 1, minus 1. Yes. Right? Okay, let me the rest of frame. Let me rest of frame. Now the equation for U, for V becomes minus M minus P of sigma minus P of minus M V P equals 0. And this becomes now the rest of frame minus 1, minus 1, minus 1, minus 1. Actually, V. Okay. And any eta and the eta minus eta is the solution. This will be the solution. And then you boost, okay? You boost this one to the final P, you get that compact solution, which is given by V equals to this one. This one will be the solution of final P. So this is the way to find the solution for Dirac's equation. Okay. But the question is how to understand it, okay? What is the physics? This is so far it's the mathematical solution by solving this equation. So how to understand this one? As you can see, yeah, let's try to discuss the meaning of these solutions. So to understand this one can try to choose the base. Let's say for C, one can choose C1 equals to 1, 0, and 2 equals to 0, 1. Okay? Because C is the arbitrary two-component constant spinor. Okay? We can choose this one and this one. Therefore, any linear combination of this and this is a good solution, right? Right? Because any arbitrary constant two spinor can be decomposed as a linear combination of this one and this one. Is that right? So this is the base. Base means the linear combination of these two is the solution. The same thing for the same thing is true for the eta. We can also do the same for eta. This means there exist 4 independent solutions in terms of. So this is for. Let me also write eta 1 equals to 1, 0. And eta 2 equal to 0, 1. Okay. This means one can choose 4. There is 4 linearly independent. Solutions. If we write as the 4 component object, let's say 1, 0, 1, 0. Okay? 1, 0, 1, 0. This corresponding to the C1, C1, okay? Because U equals to C, right? So you choose C1, 1, 0, so this becomes 1, 0, 1, 0. And U2 becomes 0, 1, 0, 1. And V1 becomes 1, 0, minus 1, 0. And V2 comes 0, 1, 0, minus 1. Okay? So sometimes to read the textbook, sometimes we include some prefactor, some overall constant here. But this is just comes from the normalization. Okay? It's not important. So for different normalizations, you can include some square root of mass. But this is the four independent. This is the four independent solutions of the equation, and the linear combination of them will also be the good solutions, right? Now the question becomes how to understand these four independent solutions. Okay, what is the relation between them? What is the relation between them? Okay. But physically, we know the Dirac equation describes the electron in our real world. Okay. And we also know electron has the antiparticle, okay, which is positron. Antiparticle means charge opposite, but the other quantum number is the same. Okay. Now we also know electron has spin up and down. So putting together, we know there should be 4 degrees of freedom, right? Because you have particle, antiparticle. Each case you spin up and down. Okay. So there should be 4 degrees of freedom, which should be related to these 4 independent solutions, right? Because this is the solution also we solve the equation motion, right? Okay. Well, you might complain that this solution seems you can easily find it just in the rest frame. That's true, because if you only want to count the degrees of freedom, it doesn't matter you work in which frame, right? It shouldn't be relevant. In any frame, the degrees of freedom should be the same. Okay. You can identify correctly the degrees of freedom in any frame. Okay. So in rest frame is enough. So for that purpose, it's not difficult, because we can see the solving the equation in the rest frame is super easy. Okay, and we got these 4 independent solutions. Okay, but very luckily, this is not super difficult in the sense that last time we already know some operations like charge conjugation. Okay, so we can try. Okay, for example, we can try to take the charge conjugation. We can take the charge conjugation, for example, for this U1. Okay. So do you still remember what's the charge conjugation for given spinner, for spinner? Because now we're working in wire base, right? We're working in wire base. What is the charge conjugation for spinner? So U1, say C, is the minus I gamma 2, right? Minus I gamma 2 times this force spinner. In this case, will be 1, 0, 1, 0. A star, right? Right? You still remember? Because this definition in the wire base for a given force spinner, this is the charge conjugation. We derived last time, okay? Derived last time. Then what you get? You can easily, you know what is gamma 2, right? Just plug it in. You check it. What is the result? You know what's the result?
1 minus 1 minus 1. Oh my God.
What is the result? Let's do it together. So this would be the minus I. What is gamma 2? Gamma 2 is 0, 0, 0, minus I, 0, 0, I, 0, I, minus I. Okay. And now let's act on this 1, 0, 1, 0. What do I get? I get precisely 0, 1, 0, minus 1. Do you agree? You can check it, right? This is the answer. So you realize what? The charge conjugation send this U1 to where? To V2, you see? To my V2, right? V2 is here. This clearly justifies the relation between them. You can also check it for U2, okay? You can also check it for U2. Clearly indicates the relation between this one, between U1 and the V2. Okay? Because we know physically charge conjugation will send the particle to what? To antiparticle, right? Because charge conjugate means flip the charge. The particle and the antiparticle should carry the opposite charge. Every other is the same. Okay. So this justifies the V2 is the antiparticle of U1. Okay. And for the other two, you can also check it. So this means that you represent the particle. Okay. And the V represents the antiparticle. Okay. You describe the particle, and the V describe the antiparticle. Now you continue to ask, what is the difference between U1 and U2? Do you know how to justify this? Yes, but how to justify this?
Sigma.
That's right. We also know the spin operator, right? You just act on it, okay? For example, you can act. We know the sigma, which is the spin operator. Last time we learned what is the spin operator, right? We know spin operator. Spin operator is a vector operator, okay? But in this case, you can, for example, you can try to act a component of this spin operator sigma. For example, sigma 3, okay? Sigma 3. And then you can justify the U1 and the U2 has opposite spin, okay? Has the opposite spin polarization. If one is up, the other is down. That's the difference. You can also check it. Not something guessed, you can really check it. So now we understand the meaning of these 4 independent solutions. The U part, U1 and the U2 describe particle V1, and the V2 describe the antiparticle, and the 1 and 2, the difference between 1 and 2, spin flip. This describes the two spin states of the particle. Right? Yeah, what I mean is, for example, you can check. Right? You can check. you can check. For example, you can act sigma 3. What is sigma 3? We read somewhere sigma 3. And act on this Kc1. And also check sigma 3 act on this Kc2. Okay? You find that this will be equal to Kc1, and this will be equal to minus Kc2. See? And now let's talk about this localization and clean sound. First, localizations. So as we see, we choose a base there. But the point is that particular choice. That's of course is not unique choice. But the point is, we want this base satisfy normalization condition. Okay. For example, one can try to denote this 1 or 2 using the index, let's say R. So we require to see R dagger D S will be equals to delta R, and for eta also, eta R dagger eta S equals to delta RS. The delta is the RS is 1, take value 1 or 2. Okay. And you can check this is indeed true for that particular case. Right. This is called the normalization condition. Normalization condition. Okay. So in this notation, one can also write my solution for U is USP with index S. This is the P dot sigma square root CS, and this is the square root P dot sigma bar. Okay, S. Okay, and my solution V can be written as VSP equals to the square root P dot sigma eta minus eta sigma bar eta S. Okay, and S can take the value 1 or 2. 1 or 2. So why I want to write this? Because I want to find the normalization for the U. I know the normalization for Kc or eta. Then I can also compute the relation for U or V. Okay, for U or V. Since this is the two independent solution, in this case, S equal to 1 by 2. These are the two independent solutions. One can try to compute something like U bar S P dot U S P. Okay, I try to compute something like this. R or S, R and S denote these two independent solutions. Okay, this is additional index. additional index. And this dot, of course, means there is a spinner index is contracted because this is U bar, this is U, okay? And what is the definition of the bar? The bar definition should be the same as the psi, right? The U comes from psi, okay? Psi bar is defined in what? In terms of what? Is in terms of psi dagger times gamma 0, right? Now U bar is the same. So U bar, to compute this object, one gets this R, because this R index is dagger, and then square root P dot C R dagger square root P dot sigma bar. But there should be a gamma 0 here, right? This is U bar, right? Okay, this is the U dagger. This is the U dagger. Okay, and there is a gamma 0, which is 0, 1, 1, 0. Okay, and then there's the US. In the last, there's the US. The US is the P dot sigma CS square root P dot sigma bar CS. Okay, so this is what you get. You can directly compute this one, okay? Compute this one. You can compute this one. In particular, for example, you get to this multiply with this one, you get this one is here. So you actually multiply with this matrix, then it exchange this upper and lower component, okay? For this four spinors, right? This goes up and this goes down, right? And then you multiply with this one, you essentially get this time this time this plus this time this one. Okay, is that clear? Now you have an object looks like a square root P dot sigma times P dot sigma bar. Is that right? Is that right? And you can easily check sigma P sigma bar. Sigma P, this P dot sigma bar times P dot, this P dot sigma times P dot sigma bar equals to P squared. Okay? Equals to P squared. Now you take one more square root. Square root of P squared is what? The log of P, right? What is log of P? That's right. It's M. Okay? Log of P is M. So you eventually get, after new steps calculations, you eventually get a 2 delta. Yes, it's a very simple result. You can check this. Okay? It's just a 2M. The delta RS. The delta RS, if they are equal, it equals to 1. If RS are different, is 0. Okay? So similarly, you can also check V bar R E dot V S P. This will be equals to minus 2M delta RS. Okay? You see? So this is called the normalization for U or V, right? The normalization for U or V. Of course, the result, the result is related to the normalization for the cosine and the eta, right? For the cosine and eta. Yeah, you can also check something like U dagger dot U, right? That's also well defined, right? The difference is there's no such kind of matrix, okay? There's no such kind of matrix, okay? you can check yourself. You get another normalization condition. You can also check the V dagger dot V. Okay. Then you get encounter this coefficient is not mass. Okay, it's not mass, but the zero component of the momentum. You get the coefficient is the P0, okay, or E, okay, energy. So this is called the normalization condition. So apart from this, you can also get some interesting relation, more interesting actually. Some other relations looks like that. You can also consider the flipped order, okay? This is the U bar dot U. Usually we think that this inner product contracts the spinor component, right? Contract the spinor index. Finally, you get some number, right? Get some number. But you can also calculate things like U bar, okay? U bar. Something looks like this. And with a sum of this S index, with S takes 1 or 2, sum from 1 to 2. You can also compute this object, right? This object. So what is this? This should be a matrix, right? Right? This should be a matrix. Why? Because this is some column. This is the row vector, right? If you do such kind of product, you'll get a matrix. You get a matrix instead of number. Is that clear? But it's fine. I mean, matrix is fine. We know how to deal with matrix. And you can check yourself. If you compute this one, then you get the P slash plus N. Okay? Clearly, this is the matrix, right? Because there's a P slash. P slash means there's a gamma matrix. Okay? E, this is the P mu gamma mu here. So this is the matrix. Now M, you can also view M in the number or a matrix. And then they add up. Eventually, this is like a 4x4 matrix. This is a 4x4 matrix. And you can also check the V times V bar similar to U, right? This is equals to the P slash minus M. Okay. These are the very, very important relations in the later QED calculations, right? Because the QED calculations there are a lot of fermions. Okay. And you have to deal with this sum, all the different types of sum. Okay. Is that okay? So we also call this is a spin sum, right? For good reason, right? Right? Because R or S, you can think that this is denoted a different spin. Okay? We call this the spin sum. Different spin. Okay? As we just defined a few minutes ago. So U and V are the particle and the antiparticle. But U1 or 2, U1 or U2, okay? In this case, we use the S to denote U1 or U2, okay? The S can equals to 1 or 2. Use S to denote the spin, different spin state, distinguish the spin state. So we also call this is a spin sum. Spin sum. But in this case, it's not really a sum, but for the different spin state ROS. Eventually, you get some delta ROS, which means for the same spin state, you get a 2n. For different spin state, you get 0. Okay, that's it. But here, really, you can perform a spin sum. then you get a nice p slash plus m or p slash minus m result. Okay. So do you have any question about how to understand the classical solutions to this equation? Well, naively, a few remarks. Naively, as we mentioned some time ago, the component of the four spinner is complex valued. Naively, you might think, okay, because my Dirac spinner has four components and each is complex valued, then 4 by 2, we get totally 8 degrees of freedom. Is that true? You have 4, right? You have 4 components. Then each is complex valued, right? Then you might think we have 8 degrees of freedom, 8 real degrees of freedom. But that's not true. That's not true. Here we can see we only have 4 degrees of freedom. You see? The particle, any particle spin up or down. Okay. We only have 4 degrees of freedom, not 8. Well, you can think the equation motion kills the half of the 8. Then you get 4. Okay? But that counting, you get 8. The number 8 comes from the off-share counting. Okay? You didn't take into account the equation motion. After you take account the equation motion, you kill half. You get 4. Okay? Indeed, these 4 independent solutions come from after we solve this equation motion. Okay. The comment. This is a comment. There's of course other ways to justify or to get this correct counting. For example, you can use the canonical approach, like phase space counting. Okay, you can just count your phase space, dimension of your phase space. That's right. And another way to, because this is the first order equation motion, which is indeed different from what we understood, either in the scalar case or the Maxwell's case. Where is my equation motion? This is the first order equation motion. As we mentioned earlier, once you decouple, okay, once you decouple this first order equation motion, you can recover the second order in terms of component, okay? But you shouldn't, the point is you shouldn't, in that case, using this decouple procedure, you shouldn't count each component are independent, right? You see? Because they are coupled equation motion. Because if I have my component, let's say psi 1, psi 2, psi 3, psi 4, okay? But because this equation motion coupled means what? Couple means this psi 1 and psi 2 are determined, okay? They are not independent, okay? After you decouple, you can get second order equation, okay? But decouple procedure might throw away psi 2 or psi 4, okay? Then you only psi 1 or psi 3 are left, okay? Then you get the second order equation in terms of this component, okay? Then you know how to connect the first order equation motion and the second order equation motion. But the tricky point is, in this coupled equation motion, the components are not really independent, right? You can see it clearly. They're not independent. So there's an overcounting, okay? There's an overcounting. If you just do the naive counting. Yeah, you can also think from that. Okay, so the next step, clearly, after we find the solution, next step, what we're going to do is to quantize it, right? quantize? So how to quantize? To quantize the spinner, again, we go back to recall about the quantization of the complex scalars. What's the reason? Because in this case, we know also there is a particle and antiparticle. But the quantization of particle or antiparticle is not something really new. We already know this happens in the case of complex scalars. Because in the complex scalars, we also have the particle and antiparticles, right? So we should learn from there, okay? We should learn from how to quantize the complex scalars. So how to quantize complex scalars? This is maybe the first problem of the midterm examination, no? Okay. So let's recall the quantization of the complex scalar. So in the case of complex scalar, how do we deal with the quantization? So apart from this standard structure, let's see, and we introduce a slightly new structure, because we know in the case of real scalar, here the second term we just have the AP dagger, right? The first term is AP, the second term is AP dagger, okay? But then in the case of the real scalar, we have AP dagger here, right? Remember that? But in the case of complex scalar, this should be correct. Why? Because if this is the case, then you take complex conjugate, you go back to itself, which is not true. So we should slightly generalize the quantization of the real scalar, okay? To make this is a little independent operator. So we should write it here is something called BP dagger, just to distinguish this operator is not quite a Hermitian conjugate of this one, okay? Okay? And there is the EIPX. So this is what happens in the complex scalar. And the complex conjugate will be now we take the conjugate of the first line, okay? We take the conjugate of the first line. Then you realize that the conjugate of this part will be the AP dagger EIPX, okay? And the conjugate of the second term will be the BP E minus IPX, okay? So this is what happened for complex scalar. And then what is the physical interpretation? The interpretation will be, and we know dagger is always the creation operator, okay? So AP dagger, we interpret this is the create particles. While BP dagger, we interpret it to create antiparticle. Okay, and the antiparticle will carry the opposite charge, and with the same mass. So this is about the structure of the quantization of the field in the case of the field, if the field incorporates both particle and antiparticle, right? So we expect there should be a group of annihilation or creation operators. Okay, it's like an AA diagram and a BB diagram. Okay, it should go in this way. Okay, it should go in this way. And now we want to push this or generalize this to fermion. Okay, fermion not only they have particle and antiparticle. Okay, but they also have spinor structure, right?
Yeah.
They also have spinor structure compared with this complex scalar. Okay, right? There's some internal structures, right, called spinor structures for the field. For the field. So what should we do? So you can imagine, so above on such kind of structure, if you now dress more of this kind of structure with this additional spinor structure, then it's done. Okay, it's not complicated. It's just you take care of the spinor structure of the spinor field. That's it. So let's try to write down. Quantization of the fermion. Therefore, so similarly, so we should have something like this. So first of all, this should be the same. This should be the same. And this also should be the same. There should be the A, there should be AP. There should be E minus I, E plus I. There should be a BP dagger. And there should be a E I P plus X. Okay? These are the same, right? You see? Now let's try to improve this to incorporate the spinor structure. Because left hand side is the spinor, okay? The spinor field. And if you just write in this way, it should be correct, right? Because right hand side cannot be equal to the left. Because left there is a spinor structure. It's the spinor field. So what do we do? Now we combine with what we found the solution for U and V, right? Right? For U and V. So what is U and V? There's an alternative understanding for the U and V. For U and V, you can think this is just a solution of the classic Dirac equation. That's fine, perfectly fine. It's okay. But you can also think about this looks like what? Do you remember? In the case of photon. In the case of photon, there's an important structure when we quantize it. It's a polarization vector, right? Remember that? This is the U and V are very, very similar to the polarization vector in the case of photon, right? So you can think of this as some spinor polarization, okay? Which is the U or V, okay? And we know when you quantize a complex field, you should address by this polarization. And this polarization function should be a function of P, right? Should be a function of P. And on the other hand, it should take responsibility to respect this internal structure of the fields. Okay? So for that reason, there's no confusion. We should put it this way. We should put a UP here, and we should put a VP here. You see, right? Because this is what we just found after we solving the equation of motion, right? There should be a UP in front of this positive frequency mode. Okay, there should be VP in front of this negative frequency mode. Okay, we're doing this way. Now we also know there is a spin. There's a spin index, right? There's U1 or U2. You should put an additional spin index, okay, for the U and also for the V, okay? So you should do it this way. Now clearly, physically, this operator, annihilation operator A or annihilation operator B, should be prepared for each degrees of freedom, right? That's what we learned before, right? After you figure out what are the true physical degrees of freedom, you should prepare the A diagram or BB diagram for each one, okay? That's what we learned before, right? So there should be also index for this one, for that reason. There should be also index here. And we think that these different indexes, are included in this field, right? Are included in this field. So there should be a sum. There should be a sum. And then that's it. Okay, that's it. That's it. Now you try to write the additional conjugate piece. Okay, conjugate piece. And of course we know what is the conjugate piece. The conjugate piece will be the psi bar, right? Right? The psi bar. And the difference of psi bar and psi dagger is only by a gamma zero matrix, right? But it shouldn't be a problem. Right? We can just choose to write it from the psi bar, not psi dagger. Okay. So psi bar will be a sum of S. This one, and let's take a conjugate. And the conjugate should be AP as dagger. And because this is a spinner, okay? This is a spinner. The spinner should respect this kind of conjugation. It should be a bar. So this should be U bar, clearly, right? This should be U bar. Yes. P. And E, and the conjugate of this one is a plus and P. And plus. And this is the B, E, as, and the V, P, as bar, E to the minus and P. Okay, that's it. So this is the formal quantization of the fields, but this is not enough for sure, right? We know that to complete the quantization, at least we have to figure out additionally the quantization condition, right? Or the permutation relation in the case of previous case, okay? So quantization condition. So what is the quantization condition? So in this case, because of the fermion, instead of to put the commutation or AA dagger or BB dagger, okay, we have to impose the anti-commutation relation, right? Because of the fermion. This is just come from statistics, okay? Did you learn the statistics, spin statistics in your maybe which course? Statistical mechanics. Have you learned the fermion? If you flip the order of the fermionic operator, you get a minus sign.
Yeah,
okay.
-1.
You learned that? Okay. So for that reason, you can easily check. Instead of impose the commutation relation, we should impose the anti-commutation relation. Okay, anti-commutation. Right? Because you can derive this one, right? This kind of thing you can. Depends on you demand what, okay? If, for example, you can. Okay, in the spin statistics, you can easily get you can easily justify whether you should impose the commutation relation or anti-commutation relation. Okay. For boson's case, you should impose the commutation relation, right? For example, you can try to using this A dagger to create a state, okay? Right? Now we're talking about the relation between A and A dagger. Now how to get this one? How do I know I should impose commutation or anti-commutation relation? The easiest way you can check it. You just use your dagger operator to create a state. Okay? You use a dagger operator to create a state. Then for different state, there is some orthogonal relation, right? You have P1 or P2. Usually P1 is orthogonal with P2, meaning you take an overlap between P1 and P2, you get delta, okay? You get delta function. Now you use this dagger operator or A dagger operator to create such kind of state, okay? Okay? And then what? And then you compute it by switch the order, okay? Right? If you switch the order, the one after switch and before the switch, they differed by a commutator or anti-commutator, right? Right? So you can easily justify which one is true, right? Using this one. So yeah, we don't have time to derive it, but just write down. So in the field theory context, as we said, we don't think this relations are derived from somewhere. But this kind of relations indeed can be justified from statistics or spin statistics. Okay. So AP as dagger in this case, anti-commute with AQ as prime dagger equals to AP as anti-commute with AQ as prime equal to DE as dagger anti-commute with EQ as prime dagger equals to EP as EQ as prime anti-commutation equals to 0. Okay? The reason is these are all the dagger or without dagger or without dagger, it should be equal to 0. Okay? Compare with the previous commutation relation, it's very similar, except the commutator are now replaced by the anti-commutator, right? You see? And the non-trivial part of this anti-commutation relation, of course, come from this AA dagger or BB dagger. AA dagger. So AP as AQ as prime dagger. In this case, we also draft by this S indices. S is the spin indices, right? This is just one more index. You shouldn't be confused. So because there's one more spin indices, so we have a dirt function at this time. And all others is the same. There's also a three-dimensional dirt function, P minus Q. Okay, and there's a 2 pi qubit in the right-hand side. Okay. So this is called the anti-commutation relation for the equation or annihilation operator for harmonic fields. So this is the quantization condition. So what's next? So following our previous logic, the next step, we should try to compute what? to quantize the field. Propagator, right? Propagator. But in order to define the propagator, we have to discuss how to define the time ordering. No. Propagator usually we focus on this Fermion propagator, right? Which is defined by the time ordering. So the next thing we want to discuss is how to compute or how to define. First define and then compute the time ordered propagator, a time ordered 2-point function for this Fermionic field, right? For this Fermionic fields. And there's also interesting story here, and it's related to this with this spin statistics. As you can see, next. Yeah, so to see the clearly difference with the bosonic field, let's again recall. Let's go first also recall complex scalar case. Okay. Remind ourselves what happens for the complex scalar if we want to compute the time ordering. Time ordered 2-point function. So in the complex scalar case, I think this may be one problem with the term examination. Take the opportunity to compute this one. So in the case of complex scalar, one can try to compute such kind of 2-point function. Okay, such kind of 2-point function. You cannot get the non-trivial 2-point function for phi or phi star phi star. Do you know the reason? There's a very, very simple argument or reason. This is the non-trivial. This is the only non-trivial 2-point function. Okay, not something else, right? Of course, you can try to compute just out of the calculation. You can see it, but there's a good reason to argue why you should consider phi star phi insert rather than phi or phi star phi star. Does anybody know the reason? There's a physical reason.
Only in this way can create an A or B particle and annihilate the corresponding one.
Well, you can do it that way, but there's a very, very simple symmetry reason. Okay, there's a symmetry reason. Okay, because in this case, phi is charged. Okay, phi is charged. You cannot have a correlation function totally carries a non-trivial charge. It's not possible. Okay. Okay. It's not possible. The correlation function has to be charge neutral. Okay. Which means that putting together all the insertions in this correlation function, the charge has to be cancelled. Okay. So therefore, phi star has to stay together with phi, because phi star carries the opposite charge, right? Phi star carries the opposite charge. So what is this? We compute this one. We compute this one. Yeah, I just plug in. Because the position for one insertion is 0, the other is x, right? So for the x part, you get an AP dagger IP dot x plus BP minus IPX, okay? And you have AQ plus EQ dagger. There's no such kind of corner anymore because X equals 0. Act on the ground state, okay? Then you evaluate. You evaluate using this commutation relation. What you get is the result. It's very familiar, right? I'm familiar with this. So this should be a minus IP dot X. Okay? Right? The familiar result. In the third lecture, we got this in great detail how to compute the problem. And you can also compute by 0 by star x, which is just to switch this insertion, okay? You switch this insertion, 2 insertions. You get this one. And then you get the result. This is the E I P dot X and P dot X. Okay. And of course, we know how to put them together, right? So if you define the time ordered 2-point function using plus, okay, this one plus this one, together with the step function, okay, together with the step function, then we know how to write this more elegantly using a 4-dimensional integral, right? With this contour trick. So let's define the time-ordered 2-point function for the complex scalar in this case. Let's define this using the z, using this step function, using a plus sign between that 2 pieces. Okay. What would be the for real scalar in this case? Then what we get is the this one E minus I E from X theta E plus E plus I E for X theta minus. Did I make it correctly? So the plus IPX is the theta minus t, meaning that when t is less. So yeah, it's correct, right? You see, so that's the theta minus t. This piece. Right? And we know how to deal with this one from the lecture, the third lecture, right? Third one, using the contour. This equals to what? This equals to, using the contour argument, this equals to a 4-dimensional quantum integral with the E IPX with the insertion I epsilon prescription plus I epsilon. Okay. And everything is good, right? And this is the familiar result. And this is comes from the calculation of the time ordered complex scalar 2-point function. Okay? This is good. Now, it's important, yeah, the final result we can justify this is Lorentz invariant. Okay, this is people X Lorentz invariant, or this is also Lorentz invariant. And this is the momentum integral measure. Okay, it's also Lorentz invariant. Why? Because Lorentz transformation, the switch some p to other p. Shouldn't change this integral measure. Now, if you just follow the definition here to try to define the time-ordered two-point function, for fermionic field, for fermion, okay, then you have some trouble. Okay. Then you have some trouble. The trouble comes from you naively follow a plus sign here. Okay. So to define that time-ordered two-point function, we use plus. You see. We use this one combined with zeta t plus this one combined with zeta minus t, right? Over there, you see? If you use this plus sign, still use this plus sign for fermion, then you get trouble.
Yeah, the plus matrix. Plus matrix.
Right. Let's say what's the way to avoid this? Okay. Yeah. Of course, the calculation for spinors is a little complicated. What happened for spinors? Let's first calculate this one. Similarly, but now with the spinor insertion. Okay. Let's calculate this one. Okay. Let's calculate it. Then you realize that this is not this is finally not a number, right? This is not a number. This is a matrix. See? This is a matrix. The sign here, the bind here. But it's fine. It's okay. Because now we're talking about propagators or two-point functions, right? Two-point functions. Two-point function has an end point. Or propagator that has end point, right? A priori, there's no reason you have to sum over the spinor indices, right? Because the component of the spinor denotes the different degrees of freedom, okay, or fermion, right? When you talk about a propagation between fermions, the endpoint can be specified to different degrees of freedom, okay? Like a spin up or down, like a particle or anti-particle, right? There's no reason to sum over them, okay? Is that clear? Whenever we see the spinor index is summed over, which means we take into account all the different degrees of freedom, right? But this is not necessary for the propagator. Okay. So for the propagator, let's just keep the index, okay, explicit, which is in this case, right? This is a matrix. Essentially means that once we calculate this object, we can get some propagation or function between the components, right? We can read off the two-point function between different components, right? That's good, right? That's what we need, okay? We don't need to sum over the spinor indices. Okay? So that's another comment. So, and then all the remaining thing is just compute this by brute force. Okay, let's compute it. Do we need a break? Yeah, let's have a break and then we'll continue. Because this is a non-calculation.
是吗？外在上它是对保护，或者说这种人他都是能画成对等类型。你得保证它是能画成对等。就是实物。它的对角阵的话，其实就是它的那个。那你就那多少层？就得是一个实的呀。
这个注意要讲啊，
画成这个，我想一下，
应该是可以画，应该反正外星系里，哦不是你在静系里，
对，有一个实的系，
变化过去应该是会，
对，
把它变好。
本质上就是说做一个轮子变换，把它变成了一个，就只有自己的方向上面写的 S。啊，你从这个多方面可以变成那个只有1和 PZ 的状态。这个状态它首先是对角阵，就是实的。
他已经找到了，
就是已经找到了。这叫先射箭再画法。
你给我说高点作业。我给你作业，高点作业。你这有高点作业吗？不是做的。给我上网。要给你个程序识别犯人做的。但是作业都直接报犯人，没有用词啊。所以我就不想办了。混口我基本上发现。哦，那边选的那个选，还有来的没人还管，我原来说的是不是有方面，原来这个太烦动。
也可是上课也是发有烦。
就可能给你点来描述你的。你有主，这个两个合在一起，我讲完，非常细，这个空间是比这个优。然后又加上一个
我就直接回家了。
那我不会加一下。拿点我快跟快烧一起，不行，快本身你这样子给一个都有一个那个，但不同的话，scalar 跟 scalar 跟你现在学不是那
特殊的别在那个课上睡觉。
那这个不太好，其实会变换。那变换本身，我觉得它是一个过程，它是一个
对于那个传运
对，这个在实在那不要在这个对，因为 PPT 非常难，像我睡觉一样。已经开了，这必须说，我也睡觉，
另外。
我在思考的但是结果不能
有道理，有作用。
对啊，对啊，
是吗？那涉及到旋转的部分。
对，spinner 是2倍。
如果硬要
跟着
涉及到旋转的部分。
spinner 合在一起。
我把它纵的一个方向变为 D。OK。
把它随着那个
把这个就是
电光火的
方向直射到地上，就转一转就好了。
这个表示就这样。先这样打。
当次变换只涉及到旋转吗？
但是迪亚克，但是或者方针对人不一样。
当次变换的话，你确实就只涉及到一个旋转和一个。
是一个思维式呀，按思维式。
我觉得也可以这么说，也可以这么说，对，因为你这个，
我只是看，不是看到。
哎，你这个怎么加一个？啊，你这横着加的。作用在一个算法上。啊，长这样嘛，对吧？第四，不是，你这作用在一个，这不要上看到这一个，这正在算法上是这个，
你都在干嘛？
一样的，说成你一种，作用在质量上，你一个质量就是一个指标。对，像有，
这不就是算子吗？不是，这是算子，对算子。
不，这个不用选量，这个不用选量。
这是个打矢量的算子，
因为你看是这样的，因为你后面上面先这个是不变的，对吧？那同样一个变化，我就来长什么长这样，我把它拆出来，是不是就变成了？对，所以就是说，我同样一个过程在一个市场上，对，我正在一个上值来。你们都玩太对吧？全打游戏，好像就这种好怎么样？这就看你说这个作用这个变换，它是作用在谁的那个5到1.73的，就看这个算，就是你要往这个来丢来的，这是一个。
它这个是一个好风，
你是不是想说是没有的？那两个带着，因为他们俩都有，还是零啊？是的，反正在那是没在，
它有那个导风没有，然后
很多这玩意儿他们是零，你有这个零啊？是，算是吧？算，
关键是
我这没那么聪明。
他学的
对啊，我是。
真就是算。
那他为什么又定义 spinner 的那个是传播值是0，然后是5 bar， 5 bar 太大。
这画不是两放一放一个小两个。
这都说了，那应该有一个 spin，对，你可以慢速的，它的变化其实你就是，
所以它这上面应该是取的。
这上面是指着反一反前往。
这血量空间是两个，
就等于
万一他说的是1维呢？
不是这样这个，
我也不知道，但我看不对他。
这个是做的，血量体系的，这是对啊，数据系统它两个。
然后你那有点，然后那个
一传出来，
我这个国际培训的时候，
血量不能点了，但是我记得是考
啊，血量那个对本身不是，
背离波是
那个做手术，血量我真的 别错乱，还考什么回用化石？这悬量本来只是一个等级，你先把它当成是一个8个那个，
这里就是
普通规范就
大于10，
它是
规范的精神性。
而且不是
我们都知道谁规范谁。
我觉得应该不是你说的那个，就这个题手啊，因为看了一遍，它这个不是一个小学的东西，不算数，其实是
悬量，我觉得悬量他们有纠纷本身属于是一个我第一集给你做后面换了一个坐标系，但是这个维度可能对，
没有区别。
从老师的关系来看，你投资你确定是
我觉得物理学习应该在我车上考，这么可以有这个手段。
任务修小镇，
任务修小镇。你先算了，这个代数。
那我看看样子，
他明白我电动学
他得用有限那个
电动力学，电动力学。
这个阿法 L
一流说，进入高等电路绝对要这个上，就算高电代你就可以用高电代电动。我让他们也说呀，我基本上稍微反正那根是历史，这不是好就是那个更没什么建筑说这样的，关键的对，就打一一般的那种。这个对是朗姆不不讲，我建议长力这朗姆不用换一个大，LAMBDA
是大于小节奏，这个我操，你做不出来，人家给老板，所以他肯定不。这你回来教课来考来赚，因为他是用坏了。
靠的，
下学期不帮他们也是过不来，基本上我可能造化，还有可能接触力比较热点体神没了，我然后开始问多位多少，我这个会注意绝对多少。大家也可以看，电子一个，它对吧？单位这个我才，然后但是阿法跟比特不看是表化，
就是它这是不同的表述，
都得。它那个第二名，它不是可以，也可以表示一。但过程的光路对现在怎么学宝？这块对他的一个讲给现在这样子，
甚至那个什么是这个思维在上最可对讲一对期末考，加起来一技巧。对，他这个屁股是不是那个叫？
在什么有多那个无聊。
神脑地震，
中文讲一最高的
我们当时有一些电脑背的几个在2.1死东西，结果后面讲考了一个技巧题。
我们可能正好在我们考这个会题标准出现。
对，
真的好像是。
还考的是分题，翻译上
是考的题，好像是很有规矩的，专业讲的是那个经典辅导，SU2代表他的今天是早上练也对。不神秘，就当什么小。
桌子灯柱，我一种困，
你想可能让很多点是两个部分是那就是这个情况出现的这个问题。
Okay, let's continue. So let's compute this one. Let's try to compute this one. Level 4. So this will be again, you just plug in, right? Like what did before. Just plug in this definition, this operator definition, in terms of the A dagger, B dagger. Plug into this 2-point function, okay? And evaluate, okay? So what you get is P, another Q, and times prime, okay, which is a spin sum. This is prime. And the bracket. Now carefully put this A dagger and B dagger. So this is AP as UP plus BP as dagger and VP as bracket. Okay, and another AQ as prime dagger. UQ R as prime. EIQ X plus EQ as prime. V bar Q as prime. E I minus IQ X act on the vacuum. Okay. This is what you get. Okay. If you plug in this operator definitions. Now the remaining thing is the count. What are the non-trivial terms, right? Right. So as we did before, so all these operators like B, all this B will carry the vacuum, right? Right, because no dagger. So only the leftover term is the A dagger and A. Is that clear? All other terms vanish. All other terms vanish. So this will be equal to P integral U integral sum spin that's prime. There will be a UPS and a UQS prime bar. Okay. They are together with this A dagger A term. So we have to compute them. So there's a UP as UQ bar S prime. Okay? But the point is, these are not the operators, as said. These are the polarization, spin polarization vectors, okay? This U or U bar are the spin polarization vectors. They're not operators. So you can move them. You can move them freely. So you can move them. We only evaluated the operators act on the state. Okay, so the vacuum state. So this is the AP as AQ as prime dagger act on vacuum. Then this is the IQ dot X. This is the number. Okay. Okay. Now I use the quantization condition or anti-commutation relation to simplify this term or to calculate this one, right? You see? In order to calculate this one, you can add AQ as prime dagger AP as, okay? As the second term, right? You can plus, right? Then you form an anti-commutator, right? You form an anti-commutation. Then you use that anti-commutation relation here. No, this. There, okay? You use the first one. Use first one. It's A anti-commute with A dagger, okay? You get a Dirac function, right? You get a Dirac function. Now, that Dirac function is delta P minus Q. Now here you have a Q integral. Then you clear this Q integral because of Dirac function. Because of Dirac function. So in the end, you get something like E integral 1 over 2 omega p sum over omega s with their delta function. There's a delta S prime. Here's the S prime sum. So there's a U P S U P bar S E to the I D dot X. Very simple result. Okay? That's what you get. This is what you get. Now there's a structure, a spin sum structure. Sound familiar? There's something like this, right? You see? Something like this. So we use the spin sum relation, which derived before. Use sum as U S P, U bar S P equals to P slash plus. Okay? Use this one. You can further simplify. This can further simplify. Okay? We don't need to worry about this one because this is a number, right? Okay? This is a number. This is the matrix, okay? This matrix is in the spinor indices, okay? Okay, it's a matrix. But if you have a number as a coefficient, you can freely move. Okay? You can freely move to the left or to the right. Doesn't matter, it's a number, okay? Right? So you can perform this sum. You can perform this sum safely. For example, you can move this in front, okay? So you can plug in this result to get this is furtherly equals to E I P dot X P slash plus E. Okay? Is that? This is what you get. This is what you get. Okay? It's slightly weird, right? If you think about this expression, right? There's a p-dependent matrix inside, okay? Okay. And outside, you have to take the p integral, okay? It's a little weird. Yeah, but you can write this into another form to get a better expression. This is nothing but a differential operator minus I partial slash plus m act on an integral, right? Then this is sounds reasonable formula or expression. See? Okay, this sounds a reasonable expression. Okay, this is just an ordinary function. You see, this is just an ordinary function. Okay, ordinary function. Now integral over p is a function of x. You see. Now you have a differential operator act on this given function. It's very verified. But they're the same, right? You can try to evaluate. You can you can first evaluate these derivatives, and then do the integral. You get nothing but the p slash plus m. Okay, you get p slash plus m. Okay, so this is only one piece. It's only this piece, right? This is only one piece of the 2-point functions. This is a particular 2-point function. So we want to use this. Okay. Yeah. We have to calculate the other piece. Which is insertion. The first insertion is sidebar x. Just flip the order, right? Just flip the order. We're going to calculate the sidebar x psi 0. Okay. This one. Okay. To calculate this one, we really want to calculate this 2-point function between the components. Okay. We don't want to like the construction of Lagrangian. We don't want to sum over the components, right? Because this is about the 2-point function, which is a propagator. No reason you have to sum over all the different particles at endpoint, 2 endpoints. Because propagator is only about which particle propagating to which particle, which degrees of freedom propagating to which degrees of freedom. Okay. Okay. We don't need to sum over all the degrees of freedom, or make the spinor index contracted over. So let's compute this one. Let's compute this one, and so what is the result? To compare with this one, let's do it by brute force. Okay. Now there is a BQ S prime V bar Q S prime e to the minus IQ dot x plus AQ S prime dagger U bar Q S prime e to the IQ x. Okay. And there is a AP as UP as plus BP as dagger VP as term. Okay. Then act on the vacuum. Okay. Do it again. Just plug in again. Plug in the operator definition for this spinor field. This is what you get. Now you count. What are the non-trivial terms? What are the non-trivial terms? Only this one, right? With this, right? You see, only this is non-trivial. These two terms, non-trivial. And eventually, like what we did there, eventually you get the result out of this calculation. you get the E I P X P slash minus M. Okay, which is nothing but I partial slash minus M act on the integral minus I e dot x. Okay. Now you can see the key point. Now you can see the key point. If we now we have two p's, right? These two p's we obtained both this one and this one. We can try to form a time-ordered two-point function. An ordered two-point function. But the point is, if we use the ordinary time ordering, meaning if we define the time ordering as a t for two fermionic fields with psi 0, psi bar, x, if we define it in the usual way, meaning t psi 0 psi bar x equal to psi 0 psi bar x theta minus t plus psi bar x psi 0 theta e. Okay, if we do it this way, then you can try to calculate it, right? This is a definition. You can proceed. We have two pieces of that result. We get two pieces of this result. You can try to calculate it. Then you calculate it. So what do you get? You will get by combining that two results, you get I partial slash minus M because the first result is minus I partial plus M, right? So that you can extract the common. Yes.
I have a question because this we have V bar V but not VB bar, and V bar V is 2M and Dirac IS. It's a number.
Yes.
The order is V bar V but not VB bar.
V bar V. Yes.
And V bar V is not a matrix but a number.
That's right. Yes. But as said, what I'm trying to clarify is we're not doing the spinor index contracted over. That's what I'm saying.
So
in that case, it's just a component. So in that case, V bar V equals to V bar with a component. There's no matrix structure anymore. Just a component. Okay.
oh.
Okay. That's what I'm saying. Yeah, we don't contract alpha beta. Okay. Now we extract a common I partial slash minus M. Okay. Then what is the remaining part is of course a key integral. This one now with a e to the minus IPX theta e minus e to the I Px, okay, times the theta minus t. Okay? This is what you get. All right? You can just check it carefully, okay? So there's an important minus sign appears here, okay? There is a minus sign. Why? Because this is a common factor, but there's some minus sign here, okay? You see? There's a minus sign difference between the two p's, which gives finally a minus sign here. You see? Okay? But if you, based on this result, if you want to use a contour trick, okay, like what we did before, okay, using contour trick to translate this three-dimensional integral to a four-dimensional integral using I epsilon trick, what you get is, because of this minus sign instead of a plus sign, what you get is a minus I plus m. Instead, you get a simple Fermion propagator type of result. You get something like this. Okay. You get something like this, right? Because the minus sign, you have to worry about the minus sign. It's a minus sign. So this is the four-dimensional integral. You can reproduce this three-dimensional integral. Okay. With the I epsilon. With the I epsilon. So you have an important additional result here. Okay. So you have something here. Okay. This is what we didn't have before in the Fermion propagator for example, the real scalar or complex scalar case. Okay. And most importantly, you see this theory is sick. This result is very sick. Why? This is very sick because this is not Lorentz invariant. Okay. This two-point function is not Lorentz invariant, which is very bad. Okay, it's not Lorentz invariant. You see, a lot no, this changes under Lorentz transformation. You can easily check. This is not Lorentz invariant. So this cannot be correct. Okay, so what was wrong? Wrong thing here is, instead of to put a plus sign here in the definition of this time order of this Fermionic field, we have to switch to the minus sign. Okay, we have to switch it to minus sign. Okay. Now you can simply argue where it comes from. Right? You can simply argue because this term compared with this term, you switch the order of the fermion, right? Then there should be appear additional minus sign. You can simply argue this way. Yeah, that's true. Okay. You can also justify in the by some other means, but the point is this should be the correct. The minus sign should be the correct definition of time ordering, okay, instead of plus sign. See? So for bosonic field, this is the plus sign, but for Fermionic field, this should be minus sign. Now, as you can easily adjust, right? If you instead change your definition, right? If you change your definition, then blah blah somewhere here, then you get a plus, right? No confusion, right? Because definition was changed. Okay, there's a sign change. Now this is plus. Now with the plus sign, this term is gone. Okay, using contour trick. Okay, you can easily check this. Then this is gone. If this is gone, then this is a Lorentz invariant result. Lorentz invariant result. This is a Lorentz invariant result. Okay. So let's take this a new correct one. Then let's erase this one. Okay. I don't need to write it again. Then this will be the result. Okay, and this will be the result. Okay. Then from this formula, one can easily read off the Feynman propagator for Dirac spinner, right? So where is the Feynman propagator? The Feynman propagator is this one, and usually we want to read off a piece-based Feynman propagator. Piece-based. So what is the piece-based Feynman propagator in this case? We simply, again, we shift this operator inside this integral, right? You shouldn't forget this one. This is the entire result. By the piece-based Feynman propagator, we really mean the time-ordered two-point function in the piece-based, okay? In the piece-based. So what is that? Then you just shift this inside. What you get is this is the minus I, there is another I, okay? There's another I. And then what you get is the I P flat plus M, okay? Plus M over E squared minus M squared plus Y up. Okay, so this is the piece-based Feynman propagator for Dirac spinner. Again, this is a matrix, right? This is a matrix. See? This is a matrix. This is a matrix. This is a matrix because now we want to describe the propagation between spinors, okay? Between spinors, okay? And spinor has a component, okay? We want to fully describe different component propagating to other component. It should be matrix, okay? Okay, it shouldn't be a number, okay? It should be matrix. So this is a matrix. This is the matrix. Okay, so we get it. We get this propagator. It's good. Now we can combine everything we have right now to write down the Feynman rules for QED, okay? Because we know the case for photon, we know the Fermion, the Fermion photon coupling, we know the Fermion propagator, okay? And then we also know from the scalar experience, we also know how to draw the Feynman diagrams, and importantly, we know how to read off the result from the Feynman diagram, okay? Okay? So it seems up to now, we are really ready to set the complete, give the complete set of the Feynman rules for the fermionic QED, which is our real-world theory. Okay. So let's try to establish this one in the remaining time, 15 minutes. Okay. So QED, Feynman rules. The first thing we want to identify the series. Okay? By QED, we really mean the series. Plus I bar E left side. This is the theory, okay? We're now talking about. Okay. This theory describes the coupling between photon and electron and also describe the dynamics of the electron and also the dynamics of the photon. Okay. And the coupling between them is included minimal coupling. Okay. It's covariant derivative. Okay. Covariant derivative. Because there is a psi bar A psi term. Okay. So covariant derivative included the ordinary derivative with a gauge field. And just to remind ourselves, when we derived previously, probably, I mean, this is actually also a problem in the immediate time examination. Okay, the photon property. We usually use this wave line. It denotes this is photon. Okay, and this propagator is the minus I over p squared plus I absolute times g mu nu minus 1 minus c. This is in covariant gauge. P mu p3, p mu p nu over p squared. Okay. And if we take a c equals to 1 gauge, then it will become minus I g mu nu over p squared. This is the photon part. Okay, this is the photon propagator. Now we also know this spinor propagator. Okay, just the word. This is the spinor propagator. Now for the spinor propagator, we use a solid line. Okay. We use a solid line and with an arrow, okay, with an arrow, 那个箭头，那个实线，还有箭头。Solid line is an arrow. We denote this spinor property, and this will be equals to I e slash just divided over p squared minus I squared plus I. Okay. And usually just the convention, okay, just the convention, because this is the graph and this is the graph. Any graph has his own convention, okay. By no means the graph is unique, right? If you want to, I mean, if you're famous, maybe. Like Feynman, if you have your own conventional graph, people may follow you. Okay, everybody has his own. In principle, everybody can have his own convention. Okay, so this is just a common accepted convention. So the common convention is that if the arrow is from left to right, we are describing the particle. Okay. If the arrow oppositely go from right to left, okay, because there is an arrow can flip the direction, right? If the arrow go from right to left, then it describes the antiparticle, okay? That's the usual convention. So to right particle, to left antiparticle. Yeah, okay. And then there's immediately confusing, slightly small confusing here. Because in the case of scalar, for example, clearly sometimes we use error to denote the flow of momentum, right? So now, suppose you have some to left arrow, okay? Which means the antiparticle. But then, what is the momentum flow of that antiparticle? So in that case, quite often we prepare two errors. Okay, we prepare two errors. The error on the solid line described with particle or antiparticle. In case the motion of the particle has different error with this solid line error, we just make additional labeling around there, okay, to say, okay, P is this direction. That's it, okay. So, yeah, but anyway, this is just a graph notation. We will see from examples to get experience. What else? This is just a propagator, right? This is just a propagator. So in the momentum space Feynman rules, we know propagator only appears for internal lines. Remember that? Okay? External line does not contribute to propagator. For P space, or momentum space Feynman rules. Okay? Remember that? But then what happened? What to do for the external line? Now for external lines, we have to specify the polarization, right? Because external lines are given particles, okay? These are given data, given particles. For example, there could be external photon line, something like this. We know the wavelength line describes photon, right? For example, if this wavelength line as the external line, meaning there's some other part, okay? This photon line attached, okay? The photon is the external line. So in this case, we have to put a polarization vector. Let's see. In the photon case, we use epsilon mu p, okay? For this. And this is kind of incoming, right? We always read the graph from left to right. So this looks like an incoming photon, right? Incoming photon. There can also be an outgoing photon, right? The photon can go in this way, okay? Go this way. Now in this case, there's also a polarization vector. We take it as epsilon mu star. This is the outgoing. Okay? Because the traditional convention is we always read the graph. The motion direction is from left to right. Okay? This establishes this convention. Now, what about the external fermion, right? There could be also external fermion. Okay? What happened for there is the external spinner? So what to do? Clearly, we have to also assign polarization structure for the external lines instead of a propagator, right? Because now we're always talking about the piece. So for the external fermion line, there could be some external line looks like this, okay? Right? What is this? In order to consistent with this should be a describe what? An incoming electron, right? Right? Incoming electron. Because this is the from left to right. So this is the particle, okay? Okay, this is the particle, which is the electron. And the antiparticle of electron is what? It's the so-called positron, okay? Positron. 电子和什么？正电子 ，OK？ 是正电子，我们把它称之为 antiparticle. So what is the polarization or spin polarization for this external? Can you read off for the discussion up to now, from the discussion up to now. What should be the spin polarization for this one? First of all, this is the particle, not any particle. It should be U, not V, right? We know U is the particle, V is any particle, right? So this should be U. This should be U. Now, so this should be USP, which is an incoming electron. Now we can also have the outgoing, okay? Outgoing electron. For outgoing electron, we should try to assign U bar as E. Okay? Now we can have also something like this. Now this error on the solid line is to the left, okay? As just mentioned, this should describe an antiparticle, okay? This should be describe an antiparticle. But since the core of this graph is in the right-hand side, right? Okay? And the time flow is from left to right, okay? So this should be described what? Incoming antiparticle, okay? And we assign the spin polarization as the V bar. So this is the incoming positive. And correspondingly, there could be also something like this. And we call it the outgoing positive. Again, important thing is for the external line, you should view this as just one given data. Okay, okay. Because for scattering process, the external particle is always something you can choose. Okay, okay. By choose you mean to collide. You can prepare some state to collide. Okay, and then to receive the outcome, you can choose to receive particular state among the outcomes. Okay, then you count the probability and the amplitude. So that's what we compute in the scattering experiment. Okay. So these are the choosing, and this spinner should be on shell. So this is the economy. Okay. This particle should be on shell. Okay. On shell. On shell means satisfy equation motion. Okay. Because we satisfy equation motion, there is a very nice constraint for those U or V's, right? Because we know equation motion impose constraint for this U or V, right? Directed. For example, you can have the P slash, and we just discussed in today's lecture. You can have the P slash minus M factor U equal to U bar with P slash minus M. These are equal to 0. And you can also have P slash plus second VV. This is equal to V bar at P. With the P slash plus M, this will be equal to 0. Okay? Without constraints. And what else? The only remaining the only remaining thing is the interaction term, right? The only remaining thing for this theory is the interaction term. So what is the interaction term? Importantly, the interaction term from there is minus e psi bar gamma mu psi a mu. This is the interaction term. Okay? This means there are two fermion and one photon. Okay? There are two fermion with one photon. You see it? Right? Now, as we discussed, since this is the Dirac fermion, this Dirac fermion can incorporate many different degrees of freedom, right? You can include the particle and antiparticle. In this case, you can include the electron or positron. You can also include the different spin state, okay? Spin particles. So, but the point is, for this interaction term, as we learned in the scalar case, we only need to read off the coupling, right? Remember that? For the interaction vortex, we only read off the coupling, contribution from the coupling. That contributes to the amplitudes, okay? So no matter which vortex, you could form very different kind of vortex. For example, you can have something like this kind of line, go to this kind of line, okay? And you have something like this. Okay, you can have something like this for sure. You can also have this line, okay, this. You can even have something like this, like this, okay. Or you can have some line, this. Okay, all the different, but no matter which vertex, since we only need to read off the coupling, so all this contribute to the minus I, all this graph contributes to the minus I. E, which is the coupling from here, gamma mu, okay? Don't forget this is also gamma mu, okay? So in this QED case, the vertex includes the gamma matrix. This is very important, okay? Okay? Because this is defined through the Lagrange, you cannot throw it away. If you throw it away, then it's not consistent, right? Because this vertex is about how the fermion interact, okay? The fermion has a component. The vertex has to include some gamma matrix, okay, in order to make everything consistent, okay? With this Lagrange. Yeah, so this is just the rules. We haven't yet seen some explicit examples. We will do it next time. Next time we'll just compute different families of graphs and try to find the result for these amplitudes. Okay. Yes.对，好的，好的。
以及它为什么这里可以
加发现它不是论文。
我们不想知道为什么可以直接加起来，就是你如果只是单纯这个表示的话，还是15个数。
它这里是有，因为它这里它是有两个算符的序，一个是那个 spinner 的序，这里换算符的序，但是 spinner 的序对，你需要在就是要在这里是这个词，就是
然后
就是相当于我讲一下，就如果我们
刚写在我的上面就我也这样。它还是一个加一个。
两个都是先加的。
那怎么如何表示这个？它也是一个 还是
我就说在下面这个。
哦，就是这个。那它的意义